A very good afternoon to all of you. I hope you people are doing well. We are having a lecture after long. Good afternoon, Jema. Good afternoon. Remember, we were talking about noise in the last few lectures. Today, we spoke in the last two classes, we spoke of different varieties of noise, their dependencies, etc. etc. This class, we are going to talk about the control of noise. This is the last chapter that we are starting in our syllabus. We'll try to finish it in two lectures, this lecture and the forthcoming lecture. Good afternoon, Kunika. So let's go ahead with today's work. We are typically going to talk about the control of noise. To control the noise, we must analyze a noise problem objectively. We need to see what is causing the noise, what is the path the noise is taking to spread out, and to whom the noise is reaching. So we must analyze a noise problem with these three aspects in mind. We will also talk about noise regulations which are prevalent. What is occupational noise and how do we rectify or shield ourselves from it? And we are going to talk about the walls and ceilings and noise transferred by them. Hello Pranav, welcome to the class. So, first is analyzing a noise problem. How do we analyze a noise problem? As we had discussed, a noise is created by some source, travel by some path, and received by some observer. We must try to identify the three things and separate them out. So this is a typical source path receiver analysis that we do in case of noise problems. Most of the sources like machine, automobiles, home appliances, trains, aircrafts, etc. There are a lot of sources of noise which are there around us. Most of the cases they can be identified easily. Path of the noise is very straightforward. Most of the time the line of sight will offer a noise path. For example, if there is a road next to your home, most likely chance is that automobile noise will reach to your home directly with the line of sight. If there is a tall building, then some noise is reflected from the tall building, and if there are edges and corners around in the building, then the sound can be diffracted. If there is a sound or a machine located in one part of the complex you are staying, then the sound can travel through the structures and reach to the other end. Sometimes the sound path can be very complex and very difficult to analyze. Give me a minute, I will be back. Receivers, most of the receivers are humans, but there could be situations where despite of where machines might also need a noise free environment. For example, a recording studio or something like that, where sound recording is done. Apart from the humans, the machines are also get disturbed by the presence of noise. So we can control the noise in various ways. Once you analyze source path receiver analysis, once you have done it, then one can control it at the source. That's the very first step to control the source of the noise. And a lot of effort is put into that, so that the because the con- control is most effective at the source. So for example, dampers are put. The dampers, what are the dampers? There are plenty of ways in which you can see dampers are being used. So for example, if there is a heavy machinery which is installed, you will find that heavy rubber pads are installed at the bottom, so that the the rubber pads act like a damper. The laptop I'm using has a rubber, very thin rubber boundary on the edges that is kept to make it noise free every time when you close it. If you look at the mixture grinder or some other noise making instruments at home, you realize that they have rubber pads at the bottom. So dampers are there everywhere. We keep the dampers, for example, air conditioning units when they are installed, they the outdoor unit are installed on rubber pads so that when they move they don't make noise. In some cases, a redesign is also offered. So machines, when they are designed, if they are noisy because of resonance noise, because of not having any dampers, needs to be redesigned. Just keeping noise in focus. In some parts of the world, machine noise levels are mandatory. So government gives that direction to all the machine manufacturers to put labels on their machines reflecting the noise levels. At what noise level does it operate? So it's very important. One can control it along the path also. First is the absorbing energy along the path. There are plenty of examples of this. One simple example is exhaust pipe of a vehicle. You know that exhaust pipes make a lot of noise, but that noise is much less than the noise that is created inside the engine. Inside an engine, be it an auto cycle or a diesel cycle, creates a huge blast, and the noise generated is huge. Plenty of that noise is deeply buried, and only a small part of that noise comes out through the exhaust. So sound absorbers are placed on the inner linings of the exhaust pipe so that the most of the sound is absorbed and very little comes out. Most of the flyovers are in the city, on both sides they have got perforated walls on both the sides. These perforated walls make two functions. They not only absorb the sound energy in those perforations, but the wall as a whole reflects back the sound towards the road so that the buildings next to the road are protected from the sound. So it is reflecting back by the barrier. They are everywhere. If you are ever, um, if you travel by, say on JJ flyover in South Mumbai, you will find that the reflectors are placed both sides, reflectors and absorbers. Any other flyovers in Mumbai, uh, for example, Dadar, etc., you will find the similar structures being placed. So the sound can be reflected back by the barriers or it can be absorbed along the path. Sound can still escape through and reach to some other point by an alternating path that needs to be avoided. There, an alternating path has to be eliminated altogether. So that is the control along the path. At the receiver end also sound can be controlled. Receiver itself or himself herself can protect by using ear protector. Typically you have seen these kind of images. You can see that person here is showing directions to a space aircraft when it is halting. He is wearing ear protectors here to protect himself from the loud engine noise of the aircraft. So, using ear protector and limiting time of exposure. So, people on such duties are not given long time of duty. They take breaks at suitable time and then come back. So that limits the time of prolonged exposure. I'm going to talk more on this in a while. And using remote sound attenuating chamber. So for example, if you're doing a recording where external sound can affect, you can do the recording in a sound attenuation chamber on an anechoic chamber or by using remote instruments so that the sound is completely blocked. External disturbing noise sound is completely blocked. And masking, obviously. Noise regulations are very important. They play a very, very important role in our lives. These are the noise regulation figures in different kind of area having different kind of codes in India. These are India figures. Industrial area daytime can have 75 dB and nighttime can have 70 dB. And then commercial area 65 and 55, residential area 55, 45, silence zone 50 and 40. You need to seek special permissions to violate these norms. So for example, in India, typically few days in Ganpati festival and few days in Navaratri festival, leeways are given. Individual institutions and people can take these permissions. For example, if there is a marriage procession, then the party can take a permission from local police station to go beyond these sound limits or noise limits for some particular amount of time. For another example, our college, which is trapped between two hospitals, if you all know, GT hospital on one side and the Kama hospital on the other side is completely in the silence zone. So anytime when we do a functions like Malhar or IMG, permission is taken especially for some hours. Typically for Malhar, these permissions are available not beyond 10 p.m. I remember once I was there, Malhar results were not declared, and the local police inspector stepped in sharp at 10 p.m., saying that you cannot use any loudspeakers to announce the final results after 10 p.m. The then principal announced the results without a loudspeaker, and obviously, very few people only can hear. Very few, those who were standing close to him, out of a 2000 strong strength standing in the first quad. So, yeah, these regulations are there, and in urban areas like South Bombay, they are very strongly followed as well. But it is sad to see that many places these norms are not followed, and as a result, people suffer. Well, another part of noise regulation is the occupational noise. Occupational noise are something which we experience just by the virtue of being there. You cannot avoid it. So, for example, if your duty is on a railway track, to maintain the railway track, you are exposed to the train noise all the time. Or if your duty is on the say runway to show directions to airplanes, then you are exposed to aircraft noise all the time. If your duty is there in a heavy machinery industry, you are exposed to the sound all the time. If your home is facing a junction, a busy traffic junction, maybe you are exposed to the noise all the time. So these are occupational noise. You cannot avoid it. You cannot leave the place and go. You have a job, you have a home, you have a place to stay. You cannot just go away. And you are exposed to the noise. How much should you get exposed to the noise? There are different guidelines. I'm presenting you one. These are the limits of the daily dose that will not produce hearing loss in more than 20% of the population. That means, on an average, if the population is exposed to these kind of noise, I'll come to it, then at least 20% of the population will suffer a hearing loss. That is what it means. How much are these noises? So if you are exposed to an average sound level of 90 dB for 8 hours a day. So remember, it's a very 90 dB is a very strong noise. Our day-to-day noise is around 40 to 50 dB, and if you are shout occasionally, then it goes to 60 to 70. 90 dB is huge. But you can see that this time drastically drops. So if you are at 100 dB, even a 2 hours exposure can make you lose your hearing. And if you are at 115 dB, then even a 15-minute exposure is harmful. So people working in different scenario look at these kind of charts, protect them, follow the guidelines, etc. So that's very important part. Exposure to These are the exposure to occupational noise. So typically, how much noise dose one is getting is calculated by these kind of formula. For example, you may not be exposed to all these noises all the time. maybe 90 dB to for 1 hour, and maybe 95 dB for 1 hour, and maybe 102 dB for 1 hour. So total how much you are exposed is generally calculated using this one. So this is the time for which you are exposed, and C1 and C2 is actual exposure time, and Tn is the permitted time. So suppose your for example, if your 8 hours is your permitted time, but suppose you are exposed to 16 hours of that noise, then you are actually taking the double of the allowed dose. That is what it means. Now we'll come to and talk about walls and floors and how do they transmit. So when the sound falls on the wall, on thick large wall, very few amount is absorbed. In fact, a lot of it is reflected and some amount is transmitted. I can always define transmission coefficient tau as the amount of sound power transmitted upon amount of sound power incident. So that is how you define the transmission coefficient. It is the ratio of transmitted noise to incident noise. Now, if you look from outside of the room, then you will always say that some amount is lost. The transmission loss is generally defined in dB, and it is given as 10 log 1 over tau. You take a reciprocal and you calculate the transmission loss. Now, walls and floors have the generally reduced transmission loss, but does it depend on it? So, if you have a normally incident wave on a wall, then the transmission loss is generally given by this formula. M is the mass per unit area or areal density of the wall, and F is the frequency. If it is a normal incidence, uh, so you can easily see that transmission loss, if you want to reduce, you have to use heavy mass, and low frequency will be difficult to block. What happens is that at some frequencies the wall starts resonating. Once the wall starts resonating, it absorbs some of the energy, and the loss or the transmission of energy becomes less. So transmission loss generally reduces at resonant frequencies. There might be diffraction of sound at the edges of the wall, and because of that the transmission loss increase. And finally, if there are cracks or holes in the wall, so if there are holes in the wall, then it increases, the transmission loss increases. Opening around pipes and ducts and cracks under doors also increase the losses. This is the transmission loss at distributed angles. So if the sound incident has various angles, then it decreases by 5 dB, the transmission loss. This is the graph of transmission loss versus mass per unit area. One can easily see that as the mass per unit area increases, or mass per unit area into frequency product, that is this product. If once this product increases, you can see that the transmission loss generally increases. But there are dents in this graph. It dips at some values. Those values are the values where the resonance occurs. So if there's a resonance occurring here or here or here, then the transmission loss decreases because some energy is absorbed by the wall itself. Finally, if there is a direct to hole in the wall, how much energy is transmitted? So I have a graph here. Here is the net transmission loss with hole, and here is the transmission loss without hole. So if there is a no hole, then the transmission, basically this graph is a straight line if it's a no hole situation. That means that is my reference point. That is a no hole situation, transmission loss is represented by this. If there is a hole whose size is in the given percentage of the total wall area. So when I say 0.1%, then of the total hall area, 0.1% is the size of the hole. So you can see that the transmission loss, net transmission loss starts saturating. That means this curve bends towards the horizontal. That means that the bigger the hole, more the energy, sound energy is being transmitted. At lower decibels, very less is transmitted, but as the decibels increase, so look at it. If, for example, let me take two cases, a no hole case. So at 25 decibel without hole, 25 decibel is being transmitted. But if you have a large hole, then the net transmission loss through the walls drop to around 2.5 decibels, and the rest of the energy just passes through the hole. That is how this graph needs to be interpreted. So yeah, in today's class we discussed about how sound is can be sound noise, how the noise sources can be classified, how the noise problem can be broken into parts, and we can tackle each parts independently. And towards the end we saw how the walls and ceilings will affect the noise. So I'm going to make a small Google Meet after this lecture. We will meet up for some discussions if any. Thank you so much.